All right, so last day of review for the semester. Woohoo! So the review questions come directly from the packet. Just a reminder, if you want to know exactly what's on the test, you need to consult the outline, which is posted on the course website. All right, so we've got a lot of solutions kind of stuff today. 10 mils acetone dissolved in 190 mils of water. What's the percent by volume? So percent by volume is the volume of the solute, right? Over what? Right, total volume, right? V total. So is it going to be 10 over 190? What's it going to be?
It's like 110 over 200.
It'll be 10 over 200, right? And then times 100, right? Because this is a percentage, okay? A lot of students will say, oh, it's 10 over 190. But remember, you need to do 10 divided by 200, okay? And then times 100. That gives you a concentration of 5%. Questions on number 1? All right. Let's take a look at number 2 and number 3. For each, calculate the pH and H3O plus concentration. Okay, so how could we get this into a pH? How could we get this into a pH? Okay, so we get POH by doing what? Negative log of that. Good. So 5.9 times 10 to the negative 8. Take the log. That would give me 7.23. Okay, how could I get that as a pH? What relationship?
You just subtract 14.
All right, pH plus POH is 14. All right, so 14 minus 7.23 gives me my pH. And then how would I get H3O plus? Concentration. What is it? It would be 10 to the negative pH, right? And does this need units? Does this need units? Yes, this is a concentration. What would the units be? Molarity, right? So that would be 1.7 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 molar. So those are the two things that the problem asked for. All right, so now we're going to do the same thing again. Oh, we didn't answer the question. Is it acidic, basic, or neutral? pH is 6.77, so that would be acidic, but only slightly, right? That's not really acidic. Okay, 0.0931 log POH would be 1.03. So what would the pH be? 14 minus 1.03, right? 12.97. Based on that pH or that POH, whichever way you want to look at it, is that acidic, basic, or neutral? That one's basic, yep. And then to get concentration of H3O plus, that's just 10 to the negative 12.97. So I got 1.07 times 10 to the negative 13th, and my units would be moles per liter. Remember, pH and POH are unitless, right? But concentrations need units. Concentration is in moles per liter. Questions on 2? Everybody good on 2? Okay. Let's do number 3. You have a 5 molar, and the identity here doesn't matter. That's potassium dichromate. We don't care what it is, though. You have a 5 molar stock solution. How many milliliters of the stock solution must be diluted in order to prepare 250 milliliters of a 0.1 molar potassium dichromate solution? Who remembers the formula to use here? What are we doing? Right, this is This is dilution, right? Dilution means taking a concentrated solution and making it more dilute. So if I took some of my beverage here, sports drink, and I added a ton of water to it, right, that would be diluting. So dilution, the dilution equation will be on your handout for your reference page. M1V1 equals M2V2, right? So let's list our variables. M1 is 5. And we want to know how many milliliters of it we want. So that's what we're solving for. M2 is 0.10, and V2 is 250 mils. Now remember when I told you, when we did this in class, originally I said, you can leave your unit in milliliters just because this is not technically a molarity calculation, right? We're not multiplying molarity times volume or anything like that. So long as you're really careful and remember to convert to liters anytime you're doing molarity times volume for like figuring out number of grams dissolved in solute or something like that. You could leave it in milliliters here if you're really careful. So we're going to solve for V1, right? So now we're just doing some algebra. So we can plug it in. So 5x is equal to 0.10 times 250, right? So x is 0.1 times 250 divided by 5, right? So that would be 5 milliliters. Now, does that make sense? Does that make sense? To take 5 milliliters of the concentrated solution, how much water do we add? Right, so take 5 mils of concentrated and add 245 mils water. Right, that's what we would do. Does everybody understand how number 3 works? All right, let's go on to number 4. We're going to do some conjugate acid-base pairs using the Bronsted definition of acids and bases. Because there are 3 models of acid-base. There's the Arrhenius model, there's the Bronsted model, there's the Lewis model. And we focused in Intro Chem on the Bronsted model. All right, so acids do what? Do they donate or accept? Well, what are we donating and accepting first? Acid does what? Base does what? Is it a donor or an acceptor for an acid? It donates, right? Acid donates, and base accepts. All right, so let's look before to after. NH3 becomes NH4 plus. So did it donate or accept H plus? It accepts, so what does that make it? A base. And if you're a base on this side, what are you on this side? That should be a double-headed arrow. What should it be on this side? Conjugate acid, right? All right, let's compare. HCl becomes CO minus. Did it donate or accept H plus? It donated, so that makes it the acid. And if you're an acid over here, your conjugate base over here. Why do you need to have an acid and a base on both sides? Well, because the reaction goes both directions, right? So I need to have an acid and a base to neutralize each other on the left, and an acid and a base on the right. Right? This is a double-headed reaction. Any questions on 4? 4. All right, let's do number 5. So this is true. When you go to the pharmacy and you buy that brown bottle, hydrogen peroxide, you know, you scrape your leg, you pour it on it, it stings, it bubbles, right? That's what you're buying. You're buying hydrogen peroxide, and it is 3%. That's a true statement. So let's go to pharmacy and get a 350 milliliter bottle. How many milliliters of hydrogen peroxide am I actually buying? Well, I'm actually buying mostly water. Let's talk about how we would do this problem. If it's a 3% solution, that means for every 100 milliliters of solution, how many milliliters are actually hydrogen peroxide? 3. So we can use that as a conversion factor, right? If it's a 350 milliliter bottle, 350 milliliter bottle times 3 mils H2O2, I should say 3 milliliter solution, right? So 350 milliliters of solution. 100 milliliters solution, right? Milliliters of solution cancel. Does everyone see how we set that up? We're using the fact that it's 3% as a conversion factor. So 350 times 3 divided by 100 is 10.5. So what did you buy? Well, you bought 10.5 mils of hydrogen peroxide, and you bought 339.5 mils of water. Right? I'm getting ripped off. Well, yeah, you are, because it's only a 3% solution, right? You're only buying 10.5 mils of hydrogen peroxide. The rest is all water. And why is it stored in brown? Because hydrogen peroxide decomposes readily, and light speeds that up. So if your bottle's been sitting in the cabinet for a year or so, that concentration's gone down even more. Does everyone see how we did number 5? Alrighty. Let's go on to 6. Formulas and then identification. Hydrobromic acid is what formula? HBr, which is obviously an acid, right? Sulfuric acid is what? H2SO4, good. Potassium hydroxide is KOH, and sodium hydroxide is NaOH, right? These two are bases, these two are acids. Questions on 6? All right. Let's look at 7. It requires us to use the solubility rules. Okay, here's what the reference page looks like. So your reference page does have solubility rules on it. Okay, so you don't have to memorize solubility rules. This is the actual reference page that you'll be given. Okay, so that's the exact reference page that you get on the test. So there is solubility provided for you. Use solubility rules to determine if each are soluble in water. If they are, write a dissociation reaction to show what happens when it dissolves. Copper 2 chloride, is that soluble or insoluble? Let's look at our reference page and find out. Chlorides, all soluble except, is copper listed as an exception? No. So would copper 2 chloride be soluble? Yes, it is. So the dissociation reaction would be CuCl2 solid becoming Cu2 plus aqueous plus 2Cl minus aqueous. Remember, this 2 comes out as a coefficient. All right, let's do B, sodium sulfate. Sodium sulfate. Here are the sulfates. These are all soluble with the exception of these guys. So would sodium sulfate be soluble? That's a tongue twister to say. The answer is yes, right? The answer is yes. So that would be Na2SO4 solid becoming 2Na plus SO4 2 minus. And lastly, lithium sulfide. Sulfide, right here. Sulfide's listed under insoluble. However, ammonium and the alkali metals, which are group 1, are soluble. Is lithium in group 1? Yes. So would sodium sulfide be soluble? The answer is yes, it would. So that would be Li2S becoming 2Li plus AQ plus S2 minus AQ. Do we agree? Questions on 7? Okay, let's do some more calculations. This time, I've got hydronium ion concentration. Don't be thrown off in the future, just FYI. Some textbooks write that as H+ concentration. Okay, so just FYI, if you go on to take other classes, some textbooks call it H+. Okay, so don't let that throw you off. All right, so let's do the calculations here. How would I get pH? How do I get the pH? pH is equal to the negative log, right, negative log. So take the log. So I got 1.7, and pOH would be what? How do you get pOH? What do I do to get pOH? Subtract from 14, so that's 12.3. Do pH or pOH need units? No. And then how do I get hydroxide ion? 10 to the negative pOH, right? So, does this one need units? Yes. And what is the unit? Right. Molarity, moles per liter. Questions on 8? All right. Well, there are specific sig fig rules for logarithms, but we actually didn't talk about them in intro chem. We get in, when you take gen chem, we'll get real scrupulous about the sig figs and logarithms, but in intro chem, I don't get obsessive about it. So in intro chem, the answer there is no. But just so you know, yes, there are rules for sig figs for logs, but we don't worry about it in intro chem. We get obsessive about that in gen chem. All right, I'm gonna need a little bit more room here, because what kind of calculation is this? This is a titration, right? Okay, so let's write our neutralization reaction first. We've got NaOH, AQ, plus H2SO4, AQ producing H2O, which is a liquid, and Na2SO4, which is aqueous. Is this balanced? No. What do I need to do to balance it? 2 NaOH, and where else do I need 2? 2 H2O. Good. Okay, now I'm told that 41.1 mils, and it's 20.0 mils here, and it's 0.150 molar. And I want to know what's the molarity of the base. All right, so titration, we have to do some steps, right? First of all, we need to know number of moles of acid. So molarity times volume of the acid. So molarity is 0.150 moles per liter. And the volume, can I leave it in milliliters? What should it be in? Liters. And what would that be in liters? 0. What? 0.02. Do these zeros go along with it? Are they significant? Yes, they are, because of that decimal place. All right, so 0.15 times 0.02 gives me 0.003 moles H2SO4. All right, now we're going to do mole ratio, right? That's step 2. And that comes from what? How do I get those? From the balanced equation. Good. So I take my number. Now, technically, I'd have these zeros tagging along here. Just got lazy. So 0.00300, because we're going to carry 3 sig figs, moles H2SO4. 1 mole is used for every 2 moles that react. So moles cancel. So I'm just multiplying by 2. Right, so that gives me 0.00600 moles NaOH. And now do I have everything I need to calculate a molarity? I do, right? Because molarity is what? Molarity is equal to what over what? Moles over liters, right? Can I convert milliliters to liters? Is that something I can do? Yes. So 0.00600 moles divided by 0.0411 liters gives me a molarity, rounding my final answer to 3 significant figures. That would be 0.146 molar. Do we agree on 9? Questions on number 9? Alrighty. Let's go on to 10. When 1.2 grams of sodium chloride dissolves in 5,000 milliliters of water, what is the concentration in parts per million? So we need to know mass of the solute over mass of solution times what? For parts per million, it's 10 to the 6th, right? Okay, so the top number is the 1.2. And how do I get the mass of the water? Well, the water is a volume of 5,000 milliliters, 5 liters, right? The density of water, 1 gram per milliliter. So that's 5,000 grams. Right? Now, do I need to add that 1.2 as well? Remember, it's total mass, right? So it'd be 5,001.2. Is that going to make a significant difference in your answer if you forgot to do that? Probably not. Probably not. Once you round it to sig figs, we'll just do it both ways just to see. 1.2 divided by 5,000 gives you 0.00024. And 1.2 divided by 5,000, 1.2. Yeah, it's once you round it, 0.20024 versus 0.002399. You only get to keep 2 sig figs, so your answer will not make a difference. Times 186. So that gives you an answer of 200, because you can only keep 2 sig figs, 240 parts per million. So what I'm saying is if you forgot to add that 1.2, once you round your final answer, you wouldn't be able to make a difference anyway. Actually, we should only be keeping 1 sig fig, right? Because is there a decimal here? Let's just pretend for the sake of argument that there is. I don't like to give you ambiguous things like that unless I'm just intentionally trying to test your ability to pay attention. Because if there was not a decimal there, what would this round to? It would be 200, right? And sometimes I am intentionally trying to see if you're watching, but I actually was not trying to trip you up on that one. Okay, let's do the next problem. More titration. It's the exact same reaction that we did a few minutes ago, too. At least we don't have to write a new problem, right? 2NaOH plus H2SO4 produces 2H2O and Na2SO4. We're still wanting to know the molarity here, and it's 25 mils, and molarity here, 5.50, and its volume is 3.8 mils. Okay, so let's go through this one. It's the exact same procedure we did a few minutes ago. So we're going to take volume times molarity. So 0.0338 liters times 5.50 moles per liter gives me 0.0338 times 5.5, 0.1859 moles H2SO4. Let's multiply by the mole ratio, which is still 1 to 2. 1 mole H2SO4 for every 2 moles NaOH. So I'm just taking my number and multiplying it by 2. So that gives me 0.37, that's a 7.18 moles NaOH. So that means molarity is then moles over liters. So 0.3718 moles over my volume, 0.0250 liters. So divided by 0.025. Keeping 3 sig figs, that would be 14.9 molar. That's pretty concentrated. Do we agree on 11? Yeah. Exactly the same procedure that we did just a couple minutes ago. All right. Let's get to number 12. What is the percent by mass? What is the percent by mass of NaCl? Solution added by 10 grams to 50 grams. Is it 10 over 50? What is it? 10 over 60 times 100. So what did you get? Do we agree? I didn't actually do it. I've taken your word for it. 10 divided by 60. Yes, I agree. Okay, let's do number 13. Remember, acid donates, acid gives, base takes, right? So HF becomes F minus, so did it give or did it take? What did it do? It gave. So does that make it the acid or the base? That would be the acid. That would make this the conjugate. Again, that's a double-headed conjugate base. And then carbonate became HCO3. What did it do? Give or take? Took. So that makes it the base and the conjugate acid. Questions on 13? All right. Let's move on to 14, calculating molarity. Molarity has what formula? Molarity is what over what? Moles over liters, right? So this is 5 grams. And we have to convert it to moles, right? So molar mass is about 180. So 5 divided by 180, that gives me 0.02778 moles. And the volume is 100 milliliters. What is that in liters? 0.100, right? Move the decimal 3 to the left. 1, 2, 3. So molarity, 0.02778 over 0.1. 0, 0. So what's my final answer? Is that going to make my number go up or go down? You're just going to drop that 0 right there, right? That's all you're going to do. 0.2778. And then I round my final answer to 3 sig figs. So that'd be 0.278 moles per liter. Do we agree? Okay, OH minus is 4.78 times 10 to the negative fifth. So I want to turn that into pH, right? So I need to calculate POH. So negative log of 4.78 times 10 to the negative fifth. So 4.78 times 10 to the negative fifth. Log of that. 4.32. So that means the pH is 14 minus 4.32. So that's 9.68. And that's what the problem was asking for. Is that acidic, basic, or neutral? Acid, base, or neutral? That would be basic. Questions on 15. Okay, let's do 16. Actually, you probably can't see if I write down here. Can you see in the back if I write right here? Okay, I'll just move it up. All right, what volume of 2.5 molar contains 0.05 moles of the cation? So if molarity is equal to moles over liters, do I have all the information I need to be able to solve this problem? I do, right? Because I can plug and I can solve for volume. So 2.50 is equal to 0.0500 over x, right? Solving for the denominator. So multiply both sides by x. So 2.50x is equal to 0.0500. So x, divide both sides by 250, excuse me, 2.5. X is 0.0500 over 2.50. Got the cursor like right in the way too. So 0.05 divided by 2.5. X is equal to 0.02. We keep how many sig figs? 3 liters or 200 milliliters. Right? Because you can't, that's not a practical volume. If I handed you a 1 liter beaker and said, measure out 0.02, you couldn't do it. You could measure out 200 milliliters though. That is a practical unit. And you would need a decimal there. But I mean, if you left it like that, that's typically correct. It's just not practical. All right, number 17. Oops. Get my numbers all messed up. There we go. To make 200 grams of a 2.8% solution, what mass of salt and what mass of water should I use? So this is another problem like that H2O2 one we did a second ago. We're using the fact that it's 2% as a conversion factor. Okay, so if it's 2.8%, that means for every 100 grams of solution, we have 2.8 grams of NaCl. Right? So if I want to make 200 grams solution, we're just multiplying 2.8 grams for 100 grams. Right? Gram solution cancels out. So that'll give us the mass of the sodium chloride. So 200 times 2.8 divided by 100 gives me 5.6. And then how would I get the mass of the water? I want the total mass to be 200. So what do?
You just subtract that.
Right. And so the mass of water is just 200 minus 5.6. Right, so minus 200. So that's 194.4 grams H2O. So you take your 5.6 grams of sodium chloride and dissolve it in 194.4 grams of water. Questions on 17? I'm going kind of quickly because I know we're running low on time. But I do have office hours this afternoon, so if you want to come talk to me, because we got going through it quickly, you can come see me this afternoon. All right, so solubility rules here. Lead 2 nitrate. So this is the molecular. PbNO3 2 aqueous plus KCl aqueous. This is double displacement, right? So the lead 2 is going to get together with the chloride, make PbCl2. And if we look at our solubility rules, we'll see that that is a precipitate. Right? Chlorides all are soluble except Pb2+. So that will be a precipitate. So it needs the subscript S plus 2KNO3. And so we need a 2 here as well. All right, that's the molecular equation. How do we turn molecular into complete ionic? Now, some textbooks call it total ionic. It's the same thing. What do we have to do? Anything with an AQ, what do? We split it up, right? And we get our charges back, right? So it's not Pb, it's Pb2+. Plus 2NO3 minus, plus 2K plus 2CO minus, produces PbCl2 solid, plus 2K plus 2NO3 minus. Is it correct to omit those charges? Would you get full credit? No, because potassium metal and potassium ion are not the same thing, not even close, right? Violently react with water versus soluble in water, see? So then how do I convert complete ionic into net ionic? What do? Get rid of the spectators, which are what? What are my spectators? Nitrate's a spectator, and what else? K plus is a spectator. So I'm left with Pb2 plus 2Cl minus produces PbCl2 solid. Questions on 18. Questions on 18. All right. Let's do 19, which is a gas speeds question. Now we're assuming that they're at the same temperature, right? Because if one was at 25 degrees Celsius and the other one was at 70 degrees Celsius, that's not comparable. So we have to assume that they're at the same temperature here. All right, so just making room for the next problem. We're going to use Graham's law, right? So that's molar mass of the bigger one over the molar mass of the smaller one, right? So hydrogen gas's molar mass is 2.016. Chlorine gas is 71. So square root of 71 over 2, you can just round. Calculator. Let's see, 71 divided by 2, square root of that, 5.95, 958. Even if you'd rounded, kept that as 70.9 instead of 71. And 2.016, your answer is still going to be the same. Right, so about 6 times faster. Does that make sense? Is that a reasonable answer? Yes, it is. All right. 20 is a gas laws problem. So we list our variables and then pick the correct gas law to use. So pressure is 5.75 atmospheres. Volume is 5.14 liters. And pressure, oops, that's pressure 1 and volume 1. And we want second pressure is 2.49 atmospheres. Wait, I have that backwards, don't I? 5.75 and X go together. And this goes 1, 4. There we go. These two are a pair, and then these two are a pair. So it doesn't really matter which one you identify as 1 and which one you identify as 2, as long as you pair them up properly. So we look at our reference page. Gas laws are on the reference page. We pick the gas law that works. Which one's got P's and V's? It's this one down here. P1 V1 equals P2 V2. So P1 V1 equals P2 V2. So 5.75x is equal to 2.49 times 5.14. So do some arithmetic here. 5.75x is equal to 2.49 times 5.14. 12.799. So divide both sides by 5.75. So x is equal to 2.23, and this is a volume, so it'd be liters. So 2.23. Ask yourself if that makes sense. You increased the pressure, right? So you smushed it. So does it make sense that the volume went down? Yes, it does. Because we didn't modify the temperature. So the only way we can increase the pressure without modifying the temperature is by compressing it. So it does make sense that the volume went down. All right, we only got 3 more. We can get through these. I was worried we wouldn't have enough time, but we're good. All right. Actually, I want to scoop this whole thing down. There we go. Now I can put it. Okay. It's so hard to know how much space to give myself because sometimes I write a lot and sometimes I don't write a lot. Okay, sample of argon gas. Originally occupied 14.6 liters. So that's V1, it's 14.6 liters at 25 degrees Celsius. And it was heated to 50 degrees Celsius, so that's T2. And we want to know what's the new volume. Okay, we have to do a conversion. What do we have to do? Convert what to what? Celsius to Kelvin, right? So what do we have to do that? Add 273, right? So this is 298 Kelvin plus 273, so this is 323 Kelvin. Now we look at our reference page. We've got V's and T's. V's and T's, V's and T's. There we go, right there in the middle. V1 over T1 equals V2 over T2. Okay, so let's just plug in our numbers. So 14.6 over 298 is equal to x over 323. So if you want to cross multiply, so 298x is equal to 14.6 times 323. 4715.8. So divide both sides by 298. So x is equal to, keeping 1 sig fig, oh no wait, 50.0, remember. 2 sig figs. Keeping 2 sig figs, that would be 16, and that would be liters. So my new volume is now 16 liters. Is that reasonable? When we increase the temperature, should the volume expand? Yes, and I even talked about this. Remember the example I gave of my bike tire, right? When I was riding it on the really, really hot surface and had a weak spot, expanded, exploded. Bad news, luckily I wasn't on the bike. When you increase the temperature, the volume is going to expand. All right, last problem. Oh wait, we got 2 more, sorry. Got y'all excited for nothing. 2 more. Okay, so this is another gas problem. We've got volume is 16 liters, pressure is 37 atmospheres, temperature is 38 degrees Celsius, and I want to know number of moles. There's only one gas law that works here. What is it? Which gas law doesn't have a before and after? The ideal gas law. PV equals nRT. So we have to do a little bit of converting. All right, what's 38 degrees Celsius in Kelvin? Plus 273 gives me 311. Everything else is fine. So PV equals nRT. R is a constant, right? And it's on your reference page. R is a constant. Here it is, 0.08206 liter atmospheres per mole Kelvin. It's on your reference page. So 0.08206 liter atmosphere per mole Kelvin. All right, let's plug in and solve for N. So P37, leaving off units because we're running low on time. 16 is equal to N. 311. So 311, well, let's do 37 times 16. 592 is equal to 0.08206 times 311. 25.52 N. So N is equal to 592 divided by 25.52. Keeping 2 sig figs, that will be 23 moles. Do we agree on 22? All right, last one. I'm just going to bang through these real quick because we've reviewed redox a lot lately. On Wednesday, we reviewed it a good bit. All right, so I'm just going to go through these real quick. 0, plus 1, minus 1, plus 2, minus 1, 0. All right, so oxidized would be magnesium, reduced would be H, oxidizing agent would be hydrogen, reducing agent would be magnesium. Do we agree? Do we agree? Yeah. Okay, let's do this one. 0, 0, plus 3, minus 2. So what got oxidized? Iron What got reduced? Oxygen. What's the oxidizing agent? Oxygen. What's the reducing agent? That'd be iron. Do we agree on B?
Yeah.
All right, for C, let's see, 0 plus 5 minus 2 plus 2 plus 4 minus 2. Okay, what got oxidized? Let's see, 0 to plus 2, that would be zinc. What got reduced? That would be nitrogen. What's the oxidizing agent? That would be nitrogen. What's the reducing agent? That would be zinc. And lastly, let's see, this is plus 7 minus 2. This is plus 1 minus 2. This would be 0. This would be plus 2. Okay, what got oxidized? Plus 1. Right, let's see. Negative 2. Let's see. Sulfur. Sorry, it took me a second to find it. And then what got reduced? That'd be plus 7 minus plus 2. That'd be manganese. And then what's the oxidizing agent? That'd be manganese. What's the reducing agent? That would be sulfur. Do we agree? Do we agree on number D? Just squeaked it out in time. All right. Have a good weekend. I'll see you for the final.